workshop, and so this week is going to be fun as the last one. So today I want to talk about unitarity and its relationship with categorical symmetries. And this is based on works in progress with Matthew Bowling. So let's start from the basics. And the very basics is that the reasons we're here today is that we started to appreciate that the standard notions that we have of zero-form group-like symmetries can be generalized in a broad sense by realizing that symmetries in quantum field theories can be thought as having some topological defects in your quantum field theory that acts on your local operators or your extended operators, right? And when you start to buy this idea of symmetries to be topological defects, then a generalization of the standard group like zero-form case is very straightforward. So you can start to have symmetries described by defects of different dimensions. So you can start to have higher groups. And more interesting, you can discover that there are symmetries which are not invertible in the sense that they do not admit an inverse defect, so that once you fuse them together, you get back to the trivial defect. So a lot of work has been going in trying to how to make use of these non-invertible symmetries and make use of the fact that the diffusion structure of symmetries can be generalized from this point of view. What I want to talk about today is that, however, this diffusion structure of symmetry is not the only important things that we need to worry about when we talk about symmetries in quantum field theory. Because when we talk about symmetries in quantum field theory, we need to remember that they need to be compatible with the pillars on which quantum field theory is based upon. And when I say this, what I actually means is that we need to worry about locality and unitarity. Well, locality is kind of easy to take into account. For a physicist, you will probably say that you can write things in terms of functional of local fields. For mathematicians, you will probably say that your defects are fully extended. Unitarity instead is a more non-trivial statement, and usually is in the form of the fact that you ask for your representations of your symmetry to be unitary. So you have something like U dagger U is equals to 1. And I want to remind that the notions of unitarity for standard group-like symmetry is a very important one and allows us to put many non-trivial constraints in theories. So say, for example, what gives us the notions of spin statistics can put some constraints on the field content on CFDs and so on. So this is fine. And then you can ask yourself, are these new kind of categorical symmetries compatible with this kind of pillars? And naively, at first sight, you might claim that unitarity is not compatible with categorical symmetry simply because you are throwing away the notions of an invertible element, which is necessary to have a notions of unitarity in this sense. Of course, this is just a very naive incompatibility, and is due to the fact that when we talk about symmetries in a categorical sense, we have changed our point of view of symmetries. And when we ask about unitarity, if you have something like this, we haven't really changed about our perspective about our unitarity. So in order to try to make sure that unitarity is compatible with this kind of symmetries, we need to have a different approach to the questions of whether these symmetries can be unitary. And to do that, I'm gonna try to make use to reformulate the notions of unitarity, making use of this idea, right? That unitarity should have something to do with the fact that your defects, that your symmetry is described by topological defects. So in particular, what it means is that there should be some notions of unitarity that has to do with the symmetry being described by topological defects. So in a sense, we would like to have some notions of unitary defects, okay? And so to have that your eventually categories that capture your categorical symmetries, you have some additional adjectives that capture these enhanced notions of unitarity, okay? And in particular, these notions of unitarity is gonna make use of the idea that these defects can be deformed into some higher dimensional space-time, right? Because the ambient space, the unitarity that we want to have is a unitarity that comes from the unitarity of the ambient quantum field theory in which your topological defects are found. And if there is such a notion, then the interesting question is whether we can find some implication of this. Physically, we can find some non-trivial statements once we start to take into account unitarity. So the talk from now is going to be divided in 3 parts. I'm going to first try to review the notions we have in unitarity in low dimensions, when we know very well how things should behave. Then I'm going to try to sketch what should be the actual generic structure in higher dimensions. And then finally, I'm going to try to talk about what are the actual applications that we have once we take into account unitarity. And I'm going to mostly focus on solitonic symmetries and make some remarks also on toothed anomalies. So let's start from the beginning. And let's start from the very beginning, which is what's the notions of unitarity in quantum mechanics, which is where we know really what is going on. The notion of unitarity is given of a unitary symmetry in quantum mechanics is the following. Let's revisit for a second. So we are going to have, say, we are in a group like case, we have a bunch of operators which commute with the Hamiltonian. We know these are symmetries, good symmetries. And then we want these operators to act in a unitary way on your Hilbert space. And we want also these actions to be possibly projective so that we can take into account the presence of a potential anomaly. Okay. And then we have an actions of these symmetries on the operators of your theory, which is just given by the standard conjugations. Now, if you take all of this into account, what you're going to find is that your symmetries describe just an algebra, which is the twisted algebra CG, twisted by your anomaly. And the notions of unitarity here is taking into account by the fact that this is not just any kind of algebra, but rather is a sister algebra. So it has some additional properties that takes into account unitarity. This is the standard thing, right? So let's now try to rephrase this in terms of topological defects. Now, these topological defects are going to be point-like, in this particular case, on one-dimensional spacetime. Well, this is just the time direction. And we need to require a bunch of things. So first of all, we need to require these defects to be actually embedded into your time directions. So we want to be able to write down these points and be able to move them around your line. So what it means is that you want to be able to compose them. So this indeed gives immediately back the fact that we have an algebra. And they need to carry some sort of orientations, which comes from the orientations of your line. So in particular, it means that they're evaluated over these points, stable points with plus and minus orientations. And this is just by taking into account the fact that you have some topological points that you can embed on the line, right? And the fact that we have an algebra now means that we can take the loop of such an algebra and get a one category with one object, which you can think about the Hilbert space of your quantum mechanical system. And you can think about the one morphism of this category here as being your operators UG, which acts on your Hilbert space.
Right. A question?
Yes.
Can there be a fusion algebra in quantum mechanics?
Yes. I guess the point is that once you take into account unitarity, things are probably all more equivalent to the invertible case. So I don't expect that there should be something very non-invertible like in quantum mechanics. And that's, I guess, that's like you start to take into account unitarity, and you get back to something that behaves nicely. In higher dimension, of course, we know this is not true, but say in 2-dimensional, we would expect that you have unitary fusion category and just standard fusion category, which are not unitary. Things here just tells you that you go back to the invertible case. Yeah. Other questions? Good. So, okay, so as I said, this is just taking into account the fact that we have points embedded into a line. Now let's take care about unitarity. And as I said, unitarity, we know the answer. Is just saying that this algebra A needs to be a sister algebra. But we want to model that using some categorical formalism so that eventually you might be able to see some structure and then be able to generalize it in higher dimensions. So what we want is to impose some notions of unitarity on these points, which is compatible with reflections positivity that you want to have on your quantum mechanical system. So in particular, you want to have some notions of the of unitarity at the level of your point, which says that once you change the orientation of your points, you want this to act as the adjoint of your operators. And this means that you have an involutions. Sorry. And then you also want, and you can view this also as equivalently as doing some sort of reflection on your line. And then you want this to be compatible, essentially, with the norm that you get by thinking about these operators as acting on your Hilbert space. And we say that once we recover all of this kind of structure, which is precisely that of a sister algebra, we can capture this thing by saying by definition that our category BA with just one object is a unitary category, which is saying that the endomorphism of the objects is precisely a sister algebra. Now let me give an example. So this is a definition that holds for generic categories. In particular, it holds for a category with just one object in this case, but it might hold for categories which has more than one object. And the standard case, which we're gonna find also later on useful, is the case of the category of Hilbert spaces, which is essentially a revamped notions of the category of vector spaces, where now the objects are finite dimensional Hilbert spaces, complex, with a positive definite Hermitian matrix, which is what captures the notions of unitarity. And this is precisely a unitary category. In this sense here. And of course, since we just modeled the definitions of a definition of some particular kind of category to recover this kind of sister algebra structures, we also recover the nice actions on our operator. Sorry.
Yes. What are the simple objects on Hilbert?
On what? Find it just to see, I guess. Sorry?
C. Where is written there are more than one object?
Well, the simple ones,
you're not talking about simple here.
Yeah.
So just understand the difference between Hilbert and vect.
Yes. Okay, here the objects are just finite dimensional vector spaces. Here are finite dimensional vector spaces with a positive definite Hermitian matrix. And this makes this a unitary category in the sense that you have a notions of adjoint, so a dagger, and you have a notions of norm for your one morphisms. Okay, and I guess that's it.
The one-to-one map between simple objects.
Yes, and this is a problem. I'm gonna go back to that later on, in the sense that these things are very similar in a categorical framework, because these notions I just gave you is sort of evil. I'm gonna comment that later on, and if you can ask questions later, I guess, on that. Okay, so this is a sort of notions that you can do in 1D, and it has to do with the fact that you want to have some compatible properties of your defects with the sort of reflections that you can do to have notions of unitarity in your line direction. So let's now try to go in 3 dimensions, and let's see what is happening. Well, now we are interested, say, to the category of topological lines in 2 dimensions. And we want to embed these lines in 2 dimensions, so we have to do a bunch of things. The first thing is that we need to worry about embed these kind of lines in a framed way. We need to make sure that we have a good calculus for when we want to embed these lines in a framed 2-dimensional plane. Of course, this immediately turned out that this category C of your topological defect lines is a fusions category. And furthermore, now since we can also deform the lines in a plane in this kind of ways, we have a bunch of additional data that, for example, tell us that we have notions of a dual for lines. And there are some other kind of maps between them that are evaluations, co-evaluations, which satisfies a bunch of identities. Okay, and all of these additional data can be rephrased in the language of by saying that since C is actually a fusions category, so it has a monoidal structure, we can deloop it in the way we did it for the algebra of before. And we can, all of data is equivalent to say that this delooping is a category which has adjoints. Okay, and this is framed embedding. So then we can keep going, and let's start to ask about unitarity. And we can ask about the unitarity of our lines in particular. And this, as we saw a second ago, we can rephrase this by saying that our fusions category is a unitary fusion category. Okay. But this is not all we need to require.
Sorry, so when C and C check are the same, do you assume that the forbidden short indicator is trivial?
No, no, I'm gonna comment that late. It's gonna be important. Yes.
Can I ask about this notion of framing? Because I may be more familiar with the notion of framing for lines in 3D. But here it seems it's the same as an orientation.
No, it's actually not, as we're gonna see in a second. What we are just saying is that we're gonna assume that we want to be able to put framed lines on a framed plane. Frame means that we know you have some global sections of tangent space, so everything behaves very well. It's the strictest notions that you can put of tangent structure, in a sense. And you don't need, and since it's a very strict notions of tangent structure that you can ask on your spacetime, you don't need to ask about having to worry about a lot of deformation that you can do of your line.
But isn't a framing a section of the normal bundle?
No. Well, depends by the definitions you gave. And the definition I gave is the tangent framing, which means that I have a trivializations of my tangent bundle. You can have like a normal framing. That's, I guess, what you're talking about. In our case, is tangent bundle.
But just to clarify, so in the last two figures, you are assuming C and C check are good.
Yeah. Okay, but as I said, this kind of conditions just guarantees me that I have a good graphical calculus for a framed defect. But instead, more generally, when we are in a two-dimensional QFT, we are worried about two-dimensional TQFT, which are oriented. So we need to account for more data that tell us that, look, we can actually deform our defects so that it takes into account about the orientations. And the orientations might allow you to do more deformations. So we need more data. And the kind of data that we need to add to our category is the fact that essentially takes into account the fact that the tangent bundle that you can have over your lines, you can do a full rotation of it, and you want to go back to the kind of sections you had. And this means that you're going to require for having a pivotal structure on your fusions category. It's just some additional definition, which means that if you take twice your dual, this needs to be isomorphic to the identity more. And finally, you want to have a notions of compatibility with this kind of orientations, with the notions of unitarity in the sense of reflections positivity. So you want that essentially the line, the reflection, I told you a moment ago, which we used to identify in unitarity in Euclidean signature, is compatible with this kind of oriented embeddings. Okay. So, and this kind of notions, once you take all of this into account, is equivalent to say that C is pivotal with unitary duals and recover the nice kind of structure we should know from physics literature. Say, for examples, that we can recover that the dimensions of our objects are positive and things like that. What I want to get, I don't want to give the details about these kind of things, but I want to get to you the idea that there are additional adjectives that you can equip your fusions category with that are telling you that, look, there is actually good graphical calculus which takes into account both of your orientations, and that makes it compatible with the unitary structure that your embedded quantum field theory has.
Can I ask you a question?
Yeah.
There's a weaker notion of these axioms that mathematicians often consider, where instead of the identity in the top, you would have conjugation by an invertible element.
What's going on here?
Yeah. So instead of asking that the double dual is isomorphic to the identity functor, you'd ask that there's an invertible object that the double dual functor is isomorphic to conjugation.
Oh, okay.
I'm just sort of
Well,
curious why this sort of picture wouldn't appear in the physical
Well, the other example I have in mind, say, is that if you're worried about lines in a fermionic two-dimensional plane, in a plane with a spin structure,
Yeah.
and in that case, you would require that, say, you have a superpivotal category. So if you do it 4 times, you're gonna get back to the identity. If you do it twice, you're gonna have -1 to the f. That might be one of the instances you're talking about.
Example.
And you're asking for, yeah, you're gonna ask and for your plane to have some more rich tangential structure, and you want your defects to be compatible with the formation with that tangential structure in general.
Yeah, you're basically, in this axiom, you're asking for too strong, or you're asking for a stronger notion than
Yeah.
possible.
Yeah, absolutely. Precisely because my assumptions right now is that my quantum field theory in 2 dimension is oriented, and they don't need to be less strict. Just put this.
I mean, the unitarity here will enforce this. If you do only reflection, then you will just get this invertible object.
Well, for the oriented, you mean?
Yes, exactly. If you do the Hermitian version instead of the unitary version, then you will get this. It gets trivialized in the positive case.
I
The
see,
invertible object.
I see.
So, okay. So just to convince you that, so far I'm just saying, look, my fusions category has a good notions, a good bunch of adjectives that guarantees me that these defect lines are compatible with unitarity of your ambient QFT and with the orientations that I can do in my quantum. So let's now try to say, what does it, so yes. I want to comment on the fact that now we can ask, how does this symmetry act on the local operators? And to do that, since we know that in general we have categorical symmetries that may interact with different twisted Hilbert sectors, to see how our fusions category may act, what we do is to start to look at the reactions on this kind of twisted sectors of Hilbert spaces on S1. And what we find is we have pictures like this. So we have our Hilbert space on S1 twisted by a possible line, and we want to act with it with some operator, say here B and A. And generally, so we want to take this down essentially to describe the actions of these lines. And and this is going to describe, right, the actions of these operators, of these lines on the operators that lives in the twisted sector. What we find is that this kind of structure here describe what we call the tube algebras, which in this particular invertible example correspond to the twisted double Dreamfield algebra. And what we find is that if we have that our C has the correct kind of data that allows to have a good graphical unitary calculus, okay, we find that this kind of algebra that describe the action on local operators between the various twisted sector as precisely a C-star algebra structure. And this is the way we interpret that our categorical symmetry is acting unitarily between these various twisted sectors of your theory. Okay. So the main point from these examples is that once we make sure that our fusions category or the category of our topological defect has the good unitary structure, graphical calculus, then we get that eventually we expect the actions to be unitary in this sense on the operators of the theories. So let me now give you what are the expectations for the general structure that we just saw being in action here in low dimensions. Well, okay, first thing, let's just look very quickly at what we already know and then see what is actually missing. So we know that our finite symmetries in D dimensions are going to be collections of operators, which are going to have some dimensions and codimensions K. And we expect, right, this n-dimensional topological defects to be captured by some n categories, and which are related to each other through this kind of relation, which is just saying that we can view n-dimensional defects as being junctions between n+1 trivial defects. And we want these to have some monoidal structure, which takes into account the fact that we can fuse this defect along the transverse k-dimensional directions. And this is just saying that we have some good categorical structure that captures the basic idea that our defects are fully extended and that can be embedded into some higher space-time. Yeah.
Structure the same as saying that you just have one -1 category.
Yeah. Or yeah, if you want to include -1 from symmetries, yeah, you can.
I mean, why do you need to talk about these collections of categories?
Well, in principle, you don't. Okay. I guess what is actually important is all of these data, once you want to have a notions of unitarity, are kind of intertwined in a non-trivial way, and in a way that I'm going to try to quickly sketch later on. So in principle, you don't need it. It's just good to remind ourselves that what is actually going on. Yeah. Good. Okay, let's now try to add unitarity into the game. And we just saw that in order to have unitarity, we expect to have a bunch of new data that our categories are equipped with. And in particular, let me let me mention that so far the picture I presented in low dimensions have two particular problems. First thing is that we had so far just an underlying assumptions of orientability, while as was mentioned before, we might ask to have more generic tangential structures. Say we might be interested to have theories which has fermions and things like that. And second is the fact that the definitions I gave you are really not very well behaved in a categorical framework, in the sense that they are not transport along general equivalence of categories. And this goes back to the example of Vect and Hilp. If you're looking at functors into Vect and looking at functors into Hilp, and you're not requiring any kind of additional properties, then the two things are going to get you the same, precisely because the objects are essentially literally the same. Every time you have a Hilbert space, a vector space, you can equip it with some positive Hermitian metric. So it gets quite problematic if you want to make these additional properties I told you about to be generalized for higher dimensions. Okay, so let's try first to say what we need to know in order to account for more generic tangential structures, which is the following. So more general tangential structure are usually in correspondence with what's so-called symmetry types, which means that you just have a group, Hn, and subgroup homomorphism into On. And this group Hn, we can see it as, again, as the sort of local rotations that you can do on your tangent space. Say, if this was SO, then you would recover the notions of orientations. If this were a spin, you would recover the notion of having a spin structure. Okay. And so in particular, we want to ask to have a relativistic theory. So in particular, we want to have at least the Euclidean equivalent of Lorentz rotations included in your group. And then we also want to include the notions of unitarity, which is captured by the fact that, as I said, we have a sort of reflection, which captures unitarity under the form of reflections positivity. So to these kind of rotations, we need to add these reflections things. So we need to ask that there exist extensions by Z2 of your group H, which we are going to call H hat. And then there is a technical remark that you want this tangential structure to behave well under changing the dimensions of your defects. But that's not particular.
What is the physical motivation for that stability condition?
This one here.
Physical motivation?
Well, the actual motivations is that you're asking to have a stable tangential structure because you know that in this setup, you can get eventually a good notions of higher-dagger categories. And we expect them to behave nicely for this kind of tangential structures. And
you're saying In the absence of that condition, you cannot formulate unitarity, and that's your motivation.
Yeah. Okay. So this is just a reminder of which kind of additional tangential structure we are interested in. So let's now see what is going on in higher dimensions. Well, as I tried to say before, like when we were trying to embed our one-dimensional lines in 2 dimensions, we did it in 2 steps. First, we worried about like being able to do a framed embedding of our lines in 2D. And then we added some additional data that captures an unoriented embedding. Okay, so let's look at the framed case. And there is a current conjecture which says, which is in this statement here, that says that the automorphism group of category with adjoints is the orthogonal group. And we can interpret this kind of a statement in the following way, which is that n categories with adjoints can be seen precisely as a good tool to formalize the notions of graphical calculus over R to the n in a framed way. Okay, and this is literally saying that, nothing more than saying that good n categories are good recipients to describe topological frame defects in R to the n. So this is suggesting that indeed n categories with adjoints is the correct framework which captures our topological defects we are interested in. In particular, in 2D, right, I said, you might remember that I said that the category BC, the 2 category BC had adjoints, and that was equivalent to having the bunch of equations which involve the evaluations and co-evaluations. And that was precisely the 2-dimensional version of this statement. And when we make this kind of statement, we are in the realm of the tangle hypothesis. And but this is not all we want, because we said, look, it's not that's why we are interested in framed topological defects, but rather we are interested about some defects which has some kind of orientation. And these orientations need to be compatible with the notions of unitarity. With unitarity. With unitarity. And the passage that we did to go, say, from a 1 category back into the 1 category here, can be precisely seen as the fact that you have a good frame calculus in R, which is lifted to a good unitary oriented calculus in 1D. Okay. Now, what it turns out, and this is based on this work here, I wrote down all the authors, since I think probably 90% of them are present in this room. It turns out that for higher categories, there is a similar way that you can equip n categories with a sort of unitary S on n hat data. Okay, and the idea is that this additional data is precisely the data that allows you to get a coherent unitary graphical calculus in higher dimensions. So the data is kind of involved, and I won't give you the actual definitions. In 2 dimensions, it looks like something like this. And let me state that if we had, as we had before, like a fusions category, and we take it looping in the oriented case, we're going to recover precisely the notions of a fusions category, which is pivotal with unitary duals. Okay, so it's going to match with what we already know. But the nice thing is that we have a notions now for any kind of dimension. And not only that, but it turns out that we can actually adapt that kind of definitions in order to account for other kind of tangential structure in the case of that satisfy the hypothesis of the previous slides. And this is good because it means that we can actually lift this kind of calculus to have a good unitary calculus for any kind of tangential structures. Okay, so making use of these definitions, we can eventually make the following claims, which is that we expect, in general, the categories that describe our topological defects to be precisely n categories, based on what I said earlier, and EK fusions, So n categories reminds that n is the dimensions of your defects. EK fusion is just saying that you can fuse these defects along the k transfer directions. And these are also now going to be h hat d dagger, which is the fact that we're going to have a good unitary calculus for this kind of defects in d dimensions. Okay, so once we have this kind of data, then the expectation is that the action on extended operators is going to be given by what we call the integration. Let me be slightly more precise. Well, as we saw in the two-dimensional case, the idea was that from a fusions category, we sort of integrated over S1. And that gives us the tube algebra, which capture how the fusions category acts on local operators. And the idea is that you're going to have some sort of higher analog of this kind of things in higher dimensions. And this is going to have the correct property to capture the actions on possibly extended operators in a unitary way. Okay, so in particular, if you take now H2B2 to be equals to S2, we're going to recover the case we sketched earlier, which is that we're going to have a tube algebra, which we know to be a sister algebra, and that's capture the actions on local operators in a unitary way. Okay, this is what we expect to be the structure. And now I'm going to try to talk about some application of this. Is there any questions so far?
Oh, that last, was that formally factorization homology or?
Yes, I mean, so what we can prove, at least in low dimensions, is that if you don't take into account unitarity, this is precisely factorization homology. The results are precisely those of factorization homology. The expectations, I guess, is that once you take into account unitarity, this should be some sort of unitary factorization homology. Yeah. Let me also make a quick shout out to Thomas Parch, who's also working on this right now in low dimensions. So,
You mean by unitary factorization homology, and what are the features that
well, that's
distinguish it from usual factorization homology?
well, we don't really know it yet. I guess the more conservative statement is, as I said, we know that this kind of action of local or extended operators matches with what you will find if you were to compute factorization homology, if you don't take into account unitarity. And then all I'm saying is that we know how to take into account unitarity at the level of topological defects of my QFT. And we expect that that we can model the action on extended operator in a unitary compatible way, following the same kind of procedure we have without taking into account unitarity. And we expect this to, in principle, to describe some notions of unitary factorization homology, but it's just a statement that we know things matches with factorization homology without taking into account unitarity. So we will we expect this to recall some sort of unitary versions by taking into account unitarity as well. Does that make sense? Or but there is no formal statement yet, if that's what you're interested in, unless you are, of course, in low dimensions. Yeah, where things are kind of easy to see that it's just adding a C star, say, to your algebra, things like that. Okay, this is the kind of structure we expect to have. This kind of
relation of MP with the extended defect.
This should be whatever links your defects. Say, yeah, again, as before, this in the here, you will integrate this. This will be S1, and will represent this S1 here. Now, if you put this on a plane, it will be just perfect, exactly what links your point, which is your local operator that sits on your twisted Hilbert space. Okay, this is the general structure. There is a lot of data, and a lot of things are kind of non-trivial. which is precisely the reason I haven't actually give you the definition of this H-hat dagger. But what I want to talk for the rest of the talk is how we can actually apply this kind of things to some kind of statement about physics. And to do that, let me first remind something, which is the following, that in the literature, particularly in the physics literature, there are a lot of statements that involve categorical symmetries that make use of, say, higher categorical versions of vect or higher categorical versions of S-vect. Now, we know that this was so far kind of good, kind of okay, although we know that these kind of theories are intrinsically framed theories, but this kind of statements were kind of okay because we know that these were eventually good recipients for, say, having or SO or spin homotopy, canonically trivializable homotopy fixed point. Okay. The point is that, as I try to sketch, is that once you take into account unitarity, the fact that your theory are not framed anymore, but rather as some other kind of tangential structure, intertwines non-trivially with the notions of unitarity. So this kind of additional data that usually you suppress once you make this kind of statements start to become kind of relevant. Okay. So in general, what we expect is that statements that involve, say, n-vect or ns-vect should be probably reformulated using some sort of dagger equivalence, so some higher dimensional versions of Hilbert spaces, which say may depend on some kind of tangential structure. So let's sketch very quickly how things are in in low dimensions. Well, in low dimensions, in one dimensions, nothing is very traumatic. Say we are interested to oriented theories when one-dimensional that can be embedded, say, in 1D, in 2D, 3D, and so on. And these Hilbert spaces are all going to be just Hilb, the category I described previously. But you are now just viewing it with as a unitary category, unitary fusions category, braided, because now you're going to think about line in 3D, and so on. So it's nothing very particular, and we expect to have same kind of things going on for spin or for the unoriented case. But things start to get more interesting once you start to go to higher dimensions. And the way we can understand it is because usually when we try to do some kind of lift, say from some Hilbert space with some particular codimensions to lift it to some Hilbert spaces in some higher codimensions, this is literally saying that we want to ask for the kind of TQSTs that are described by this category to have a good unitary graphical calculus also in higher dimensions. And in general, this might not always be the case. So we can take, for example, the case of unitary oriented TQFTs, which are invertible. And in particular, and we can find precisely that we're going to have different classifications depending on the dimensions, the codimensions of this defect. So in particular, we can try to look at invertible TQFTs, thought as TQFTs in, say, 2n dimensions that are not embedded into some higher spacetime. And we know that the classifications, this is given by Fried and Hopkins, is given by this standard part given by some cobordist group. Plus we get the Euler theories, right? Which is just given by theories whose partition function is given by the evaluations of your characteristic class as the exponential of some real number, positive. However, now say we are interested about this theory to be embedded into some 2n+1 dimensional spacetime. And then now what we need to require is that this theory is to be compatible with the graphical calculus that you have in 1 dimensions higher. What does it mean? It means that you want these defects to be deformable in one dimensions more. And It turns out that these theories are fine. You can actually deform it into n+1 dimensions. However, the Euler theory, you cannot deform it anymore, precisely because if you evaluate it, say, on a sphere, and you're going to find some non-trivial result, which is different from 1, which is what you will get if you were to evaluate your Euler TQFT on a point. But this means that your Euler TQFT, once you think about it as being a surface of codimension 1 into some higher spacetime, you cannot actually deform it down to a point. So it cannot be retained once you look at some Hilbert space with non-trivial codimensions. And if you think about it, this is a very important property, because this is precisely the kind of deformations that we need in order to have our defects to act, to be able to act by linking on local operators, right? So the fact that we need to be able to lift our graphical calculus in higher dimensions is precisely a condition that guarantees that you can act correctly on the extended or local operators of your field. Okay, so I just reviewed like how things are for, say, for Hilbert space in the oriented case. Now let me go to the actual applications and try to make use of these things I just told you about. And in particular, I'm going to say something about solitonic symmetries. So what are solitonic symmetries? Well, solitonic symmetries are symmetries that classify the topologically non-trivial soliton configurations of a sigma model, say generically in d+1 dimensions, with some target. So we may have that our field has some non-trivial configurations, say for example on a line, and our solitonic symmetries are going to capture this kind of non-trivial configurations by assigning some charge to this kind of soliton. And we can think about the solitonic symmetries as being some TQFTs coupled to the target of your sigma model, which are now embedded in d+1 dimensions. Okay, and recently there was this very interesting reevaluations, classifications of this kind of symmetries, which arrived to the conclusions, to the suggestion that this kind of solitonic symmetries are of this kind of form, so are labeled by some kind of functors of your target of your sigma model, now seen as a groupoid, into, say, the d-dimensional versions of VEC or as VEC. However, as I said before, this doesn't really take into account unitarity. And we expect that unitarity should change these kind of classifications. In particular, we know from examples that the invertible part of this kind of solitonic symmetries should match with some covariance classifications in the unitary. Here, when we write these things, we are really implicitly saying that these defects are unitary from Reed-Hopkins classification. So what's the natural claim is that we should change the statement of before by replacing our d-vect with some versions of our Hilbert spaces, which now takes into account unitarity. And once we do this, we have essentially by constructions the fact, at least, that it makes a good match of the unitary of the invertible part of the solid. So we can try to compute some examples. Say, for example, we can try to compute the solitonic symmetries of a gauge theory in 3D. We now think about our target BG as sort of target for your solitonic symmetries. You try to compute what are the solitonic symmetries. Now you're going to get some unitary representations. And what you find is that your classifications, for example, reproduce the nice classification we know that of magnetic symmetries and its condensations. Okay, this is just an example. It's not particularly illuminated to look at the details, but what I want to comment is the fact that actually when we start to take into account unitarity, these things make things much better behaved. So in particular, when we made the initial statement that solitonic symmetries were classified by some functor into, say, d-vect, we had to make particular non-trivial assumptions, which we had to suppose that our target of your sigma model had to be pi finite. And this is quite a restrictive hypothesis if you're a physicist, because a lot of times you want to talk with something which has not finite homotopy groups. The particular and probably easiest example you can ever think of is, say, the three bosons in 2 dimensions with target S1. Now, S1 is, as you know, right, has pi 1 equals to Z, so it's not really a pi finite space. But it's so easy that from physics, we know what we should expect, right? And indeed, if you try to compute what should be your solid tonic symmetry classifications without taking into account unitarity, you're going to find rep of Z, which is something which is very problematic. However, if you start to take into account unitarity, you're going to recover precisely the good classification that you'd expect. So you're going to recover the winding symmetry, precisely because now the solid tonic symmetries, unitary ones, are going to be given by unitary representation of that. You can sort of think about it as being a sort of U1 graded versions of Hilbert spaces. So what is it telling us? Well, it is telling us that taking a unitarity into the game, it allows us to say something which otherwise probably will not be possible, okay? Even if in some simple setups like this.
This example, this rep dagger, that's just Z-graded Hilbert spaces? Is that what you're saying?
No, it's U1 graded Hilbert space. Yeah. You look at the objects, you see that these are just phases essentially, right? Okay, and this was like a basics example. And then we can try to play with some more complicated non-pi finite spaces. In particular, say we can look at the CP1 example in 4 dimensions with space structure. And indeed, what we are able to recover is that precisely we are able to recover the Q mod set symmetry that is well known to be there from literature. And this is precisely by taking into account unitarity in the whole game. Okay, now, since I guess I don't have much time left, probably, let me go very quickly and make some other kind of more general remarks about toothed anomalies. So, as we said before, like the classifications, say for solid tonic symmetries in particular, but more in general, a lot of things, seems to be affected by the fact whether we are taking into the game unitarity or not. And we know this to be true very well in the case of toothed anomalies. So say we are interested to group-like anomalies. Well, we know that its classifications can be vary from the case where we have a unitary or theory, or whether the theory is not unitary. In particular, give you some example here, and let me say that the classifications is different both in the perturbative and in the non-perturbative case. So this already suggests again that taking them into account unitarity, even in this kind of topic, is something that is quite important to consider. Okay. So for the group-like case, we can think about toothed anomalies also in the following way, which is the fact that your quantum field theory in general should depend on some weak homotopy class of your space-time, say into the fields you want to couple it into your symmetry. So you're classifying space of your global symmetry. Okay. However, the notions of a toothed anomaly can be seen as the fact that your quantum field theory do not depend on the class of such maps, but depend on the actual kind of maps you're choosing. Where the choice of the map here can be understood as a particular representations of, saying, a flat bundle in terms of particular defects. Now, when we say that your theory depends on the map rather than the class, we are literally saying that in topological equivalent flat bundles, that you can get different results whether you're trying to represent your flat bundles using a particular representation of defects, or or another one. Say the case of 2D theories, right, with as you choose symmetries, the anomaly can be seen as the fact that you are sort of doing a change of the representations of your defects locally. Okay, and this is something that goes on also for the Tooth anomaly of non-invertible symmetries. In particular, right, take the simplest example, which we know is anomalous, which is, say, Tambari-Yamagami for Z2 squared. And now let's consider the case that we can have a non-trivial Frobenius Schur indicator. It's given by plus or minus. And we know, right, that if the Frobenius Schur indicator is equals to -1, then this kind of categorical symmetry is anomalous, because this cannot be realized by an SPT essentially. And the argument, you can make the argument that your self-dual defect, so the having a non-trivial Frobenius Schur indicator is an indication of whether you have your fusion category is anomalous or not. And the way you can understand your Frobenius Schur indicator is given by the fact that you may have a situations like this where you have your self-dual line, and you want to make it straight, you want to deform it and make it the identity. And what you find is that this is not always equals to the identity, but in general is equals to identity up to this Frobenius Schur indicator, right? And this is precisely telling you that your unitary graphical calculus is not only, it can be a bit subtle and can't hold the informations about the anomaly. But what I want to make the remark here is that this Frobenius Schur indicator for unitary fusions categories, okay, different notions of unitarity, is constrained by the fact that it needs to playing well with the notions of unitarity. That's given by the fact that you're identifying some evaluations of some dagger of some co-evaluations. So again, this is a reminiscent fact that the unitary structure start to play a role into the notions of tooth anomaly also for unitary for non-invertible symmetries. So this seems to suggest that also tooth anomalies for non-invertible symmetries may need to be the definitions needs to be reformulated in order to account for unitarity. In particular, in 2D, we know that this should be seen as an abstraction to fiber functors. And the natural suggestion is that in order to account for unitarity, this should be actually substituted by having an abstractions to some sort of unitary functor into the correct versions of your Hilbert spaces. Okay. And this, of course, is bound to the existence of having some unitary SPTs that can realize this symmetry rather than some generic SPD that might not be unitary. So with this, since I think my time is almost up, let me remark that I hope to have made clear that unitarity is kind of an important thing that we need to worry about for categorical symmetries. And in particular, it can affect quite a lot the classifications results that we have. And quite nicely, the story is that once we start to account for unitarity, the nice thing that we get is that we naturally have inclusions of more generic structures rather than just the orientations structure, which is what we mostly talk about. And with that, I think.
Had some nice questions already. We have time for one or two more.
So I have a general question. So for invertible symmetries, you can have like unitary symmetries and unitary symmetries. So for non-invertible symmetries, I guess you have like more non-unitary symmetry, very relaxed.